Hello everyone. In the previous class we discussed about field extensions. And we knew that if f is a subfield of k, then k is called the extension field of f. So in this class we're going to discuss about algebraic and transcendental extensions. Suppose if k is a field extension of the field f, then an element of a extension field, say alpha, is said to be algebraic over f if alpha is a root of non-zero polynomial of f of x. That is, f of alpha should give you 0. If there exists no such non-zero polynomial, then such alpha is called as transcendental over f. In the case of complex number set, an element alpha belongs to C is said to be algebraic number if it is root of non-zero polynomial which is having rational coefficients or integer coefficients, because we know that every integer is rational. So that's the reason, even though it might be a integer polynomial or rational polynomial, if it is root of such polynomial, then alpha is called as algebraic number. And note that if this polynomial f of x, which is in z of x, is monic, then alpha is called as algebraic integer. And if any of the alpha, which is not algebraic, is called as transcendental number. For example, in the case of a complex number, we knew that e, pi, etc. are all transcendental numbers. For example, let's consider a number root 2 plus root 3. And in fact, this is algebraic. We knew that this is a real number and it is algebraic over Q. Why? Let us assume this as some alpha and send this root 2 to this side and square on both sides. Then we are going to get alpha minus square root of 2 whole square, which is equal to root 3 whole square. Upon expanding this, we are going to get alpha square minus 2 into 2 root alpha plus 2 equal to 3. And send this one to this side. So, and this one to this side. We'll get alpha square minus 1 is equal to 2 root 2 alpha. Remember, this is a polynomial, but the coefficients of this polynomial are not rationals. We need to show that this is algebraic over Q. That means there must be a rational polynomial, that is, the polynomial having rational coefficients for which this will be a root. So here, this is not a rational number, this is irrational. Now again, square on both sides. So if you square on both sides, and if you apply a minus b whole square formula, then you're going to get this is equal to square of this, that is 2 square into root 2 whole square is 2 into alpha square. So which gives you this much. Now this is a rational polynomial. So for this polynomial, say x to the power of 4 minus 10x square plus 1, for this polynomial your alpha is a root, because when you replace x by alpha, you're getting answer as 0. So your f of alpha equal to 0 in that fashion. So for this polynomial, your alpha is a root, and this polynomial is having coefficients from rational numbers. Therefore, your root 2 plus root 3 is algebraic over Q. So this is how you need to verify whether the given element is algebraic or not. Now, I had given certain problems. You just work it out and write this as assignment. Now let us define what is meant by algebraic extension and transcendental extensions. Any field extension K over F is said to be an algebraic extension if every element of K is algebraic over F. That means every element of alpha, every element alpha which is in K must be a root of some non-zero polynomials of f. Non-zero polynomials of f of x. Otherwise, this field extension is called as transcendental extension. That means even if one of the alpha in K is transcendental, then this extension becomes transcendental extension. Remember, if every alpha is algebraic, then this extension is algebraic extension. Even if one of them is transcendental number, then transcendental element, then K becomes transcendental extension. Examples: C over R, we knew that R is also field, C is also field, and R is subfield of C. Therefore, C is the field extension of R, and in fact this is an algebraic extension. Why? You consider any element of C, that is, any element in C must be of the form some real part plus I into imaginary part. Let us say A plus IB. Then this will be a root of this non-zero polynomial. You assume this as alpha, then alpha is equal to A plus IB. Send this A to this side. Alpha minus A will be equal to I into B. Square on both sides. You'll get alpha minus A whole square equal to I square is minus 1 into B square. So alpha minus A square is alpha square plus A square minus 2 alpha A is equal to minus B square. Then if you send this one to this side, that becomes alpha square minus 2A alpha plus A square plus B square equal to 0. So if you replace alpha by x, you will get x square minus 2ax plus A square plus B square. For this, your alpha will be a root because right hand side of that is 0. Therefore, every number of C is a root of some non-zero polynomial of R of x. These are real coefficients. Similarly, Q of I root 2 over Q, we know that both of them are field and Q is contained in this. Therefore, this is an extension field, is an algebraic extension. Why? Because every element of this is of the form A plus I into root 2B, where A and B are rationals, is a root of some non-zero polynomial. As we proved that A plus IB is a root of some non-zero polynomial by the same steps. Assume this is equal to alpha and solve it. You'll get a polynomial like this. For this polynomial, if you replace x by alpha, this gives you 0. Therefore, and the coefficient of this polynomial is rational. Therefore, every element of Q of I root 2 is a root of some non-zero polynomial of Q of x. Therefore, it is algebraic. So, every element is algebraic. Hence, this extension is an algebraic extension. And what about real number set over rational set? We knew that Q is subset of R, but you should note that E and pi are transcendental over Q. That means there is no rational or integer polynomial for which your E and pi are roots. Therefore, this extension is a transcendental extension. Now, let's prove a proposition which says any finite extension is an algebraic extension. So what it says? Any finite extension is an algebraic extension. Okay, let's prove this. So let us remember, if K is the field extension of F, then in fact K is a vector space over the field F. Therefore, the degree of the field extension is nothing but dimension of the vector space K over field F. Now, we have to show that any finite extension is an algebraic extension. So let us consider K is a field extension over F and it is finite extension. That means the dimension of K over F is some finite number, let us say some n. Therefore, there exists n elements in the basis which are linearly independent and spans K. Let us consider one element alpha belongs to K. We have to show that this extension is algebraic. This extension becomes algebraic if every element of K is algebraic. That means we have to show that for some alpha, we have to show that alpha is algebraic. If you want to show alpha is algebraic, then we have to show that there exists a polynomial defined over F for which this alpha is a root. So let us construct that polynomial. Now let us consider n plus 1 elements, say 1 alpha, alpha square, etc., alpha to the power of n, all are in K, because K is a field, closure law under multiplication. Because of that, if alpha into alpha, which is alpha square, comes in K, similarly, go on proceed, all of this comes in K. And since the dimension is n, because of the properties of vector space, the n set of vectors are linearly independent, but n plus 1 elements will be linearly dependent. Therefore, these n plus 1 elements are linearly dependent. That means, if you write their linear combination equal to 0, then at least one of the scalar will be non-zero over F. Say, there exist scalars a0, a1, etc. up to en, which are in F, then not all of them are 0, such that their linear combination is 0. That means at least one of these are non-zero. If one of these are non-zero, then this is a non-zero polynomial, because this cannot be equal to 0, because one of the coefficient is non-zero. Therefore, now see here, what is the root of this polynomial? Root of this polynomial is alpha. So we are having a non-zero polynomial for which your alpha is a root. Therefore, we obtained a polynomial for which alpha is a root. Therefore, alpha is algebraic. Hence, every element of K is algebraic. Therefore, K over F is an algebraic extension. So, in general, every finite extension is an algebraic extension. For example, see here, C over R. We knew that C over R is a finite extension because we need only 1 and I to generate C from R. Therefore, basis consists of 2 elements. Therefore, dimension of C over R is 2, as we discussed in the earlier classes. Therefore, this is a finite extension, and it is an algebraic. So, this completes the proof of this proposition. Thank you.